Welcome back to the wonderful world of pH and aqueous solutions. And today we're going to talk about determining the pH of aqueous salt solutions. And what we mean by a salt is going to help us define why we would talk about these differently than possibly purely a weak acid or purely a strong acid or purely a weak base or purely a strong base, because we previously have talked about those. So in this video, hopefully we're going to be able to calculate the pH of an aqueous salt solution. And we're going to see it's an ionic compound, a specific type of ionic compound. And then we're going to be able to relate the Ka and Kb, the acid ionization constant, and the base ionization constant of a conjugate acid-base pair. So let's first go ahead by defining what we mean by a salt. A salt is not just sodium chloride, right? A salt is any ionic compound that does not contain hydroxide or oxide as one of the ions. So for example, if I look at sodium hydroxide, that would not be a salt. That would be a strong base. Likewise, sodium oxide would not be a salt. Whereas sodium bromide would be a salt. Or any of these other examples here, we could have polyatomic ions like nitrate. We could have polyatomics like ammonia. We could have just a single metal and the acetate ion, or we could have a 2-to-1 ratio where we have calcium hypochlorite. So again, we're looking at these and we see that we have an ionic compound, and we're just looking to see, do we have hydroxide or oxide? And that would be a hint to let us know it is not a salt solution. Now, what does it mean when we have a salt dissolved in water versus something like HCl or maybe HClO, or our sodium hydroxide, or maybe something like ammonia, right? So each of these, we notice these are, with the exception of this ionic compound of our strong base, these are all molecules. And those molecules could either donate a proton or they could accept a proton. And again, these are neutral molecules. Now, how does this differ to a salt? Right? A salt, we notice, is an ionic compound. Now, it contains, if we look at these, each of these contain two different ions, right? We have the ammonium and bromide ion, the potassium and acetate ion. So they contain two different ions. So when we're trying to identify the pH of a solution, we need to think which of these ions, if any, are going to actually affect the pH. Will they react as a base? Will they react as an acid? So can they accept a proton or can they donate a proton? And so first off, we need to identify what ions are present in the solution when the salt dissociates. So we're going to work through these 4 different steps here when we go ahead and look at our example. So our example is we have NH4Cl. So first step, we need to figure out, before we can identify if it's acidic, so do we produce H3O plus? Is it basic? Do we produce OH minus when it's dissolved? Or is it neutral? Water is still the best acid or base. Again, we've added something that's so much weaker than an acid or so much weaker than a base than water. So again, we first find out, well, what are the 2 ions that we would get when it breaks up? So here we would have the ammonium ion and the chloride ion. So again, this is helpful for us to know some of our polyatomic ions, thinking about the ions that we would have present in the specific substance. So now it breaks up into ammonium and chloride. The next step is we need to look at each of these ions separately. So we're going to look at the ammonium ion and we're going to look at the chloride ion. So first we're going to look at our cation. So our cation is our positive ion. We need to figure out, is it the conjugate acid of a weak base? So if we think this is our conjugate acid, we would think, what is its conjugate base? So again, to get from an acid to a base, we take away an H plus, and we notice that we would get NH3. And we look at NH3, and NH3 is a weak base. Now, what does that mean for us? That means that in solution, we would have this weak base. It likes to hang out. We will actually observe NH3 in solution. It's not something that stays completely ionized or completely dissociated because it is a weak base. And so that would mean that this weak acid here of our NH4 plus will want to donate an H plus to give us NH3. Okay, so that's our first step. We would say yes. Okay, we've answered yes here to question 2. It is a conjugate acid of a weak base. So that was our first ion. Let's then go and investigate our second ion. We need to figure out if our anion, again our negative ion, is the conjugate base of a weak acid. So again, if this is our conjugate base, we want to look at, well, what would be its conjugate acid? So we're going to add an H plus, right? We gain a proton to go from a base to an acid. And that would give us HCl. And we look at HCl and we know that HCl is a strong acid. Now, what does that mean for us as we're thinking about the formation of this? So we ask ourselves, if Cl minus reacts, what it's going to do is it's going to produce HCl. Now, what do we know about HCl? HCl is a strong acid, and we know HCl is always 100% ionized in water. So if I add HCl into water, it would always be 100% ionized. It's never going to want to, quote unquote, unionize. It's never going to want to go from Cl minus to HCl. So we notice that that reaction is not going to happen. So what reaction will happen if we know that our NH4 plus is going to act like an acid here? Well, let's go ahead and write this out. We're going to have NH4 plus, and it's going to react with our water here. And if we look at the fact that we're saying that this is an acid, that means it's going to donate a proton to water. When it does, it's going to be left over with NH3 and H3O plus. And so we notice because this weak acid here, it's going to form our NH3, which is also a weak base. Unlike our strong acid, it is not 100% ionized like that strong acid. It will form in solution. So this reaction is going to occur. And when it does that, it makes H3O plus. As it makes H3O plus, that means it's going to make it into an acidic solution. Okay, so then if we found that neither one of these react, that's the fourth step here, we'd say that water still remains our strongest acid or base, and that would mean it's still neutral. We're going to have this neutral amount of hydroxide and hydronium. So now what I would like for you to do, I'd like for you to pause and practice. I want you to go ahead and determine if the solution created by these 3 salts is going to be acidic, basic, or neutral. And just like we did before, if the solution is not neutral, why don't you go ahead and write out the reaction that actually changes the pH, kind of like we did up here. So why don't you go ahead and pause and do this, and then once you've written them out and tried them on your own, unpause, and then you can see how I thought through it. So now that you've had a chance to think about it and practice this on your own, again, we look at our 2 ions that we have here, K plus and NO3 minus. And again, we look at our positive ion and we ask, is this the conjugate acid of a weak base? Well, to get to the weak base, right, we have to take away an H plus. Now, what do we notice about K plus? There's no H plus. So what that means is that it has no capacity to act like an acid. So this ion here, the K plus ion, cannot react as an acid. It has no ability to do that. It doesn't have an H plus, right? There's no H plus available for it to donate. So therefore, it cannot react as an acid. So now we know our K plus is not going to do anything to the pH for our solution. Then we go to NO3 minus. We look and see what is the NO3 minus, what is the conjugate acid of NO3 minus. So we're going to add an H plus, right? It's going to be a base to give us HNO3. And we look at that acid that we possibly would form, and we see HNO3. That is a strong acid. And what that means, since it is strong acid, it will not form from the reaction of water with NO3 minus. So we notice is that neither one of these ions actually are going to react as an acid or as a base. So that would tell us that our solution here would be neutral. Okay, neither one of those are going to react as an acid or base. Let's go ahead and go to our next one here. We have KNO2. So now we have K plus, NO2 minus. Now with the same analysis that we just did here, we can make the conclusion our K plus is not going to do anything. So we can go ahead and rule that out as a possibility. And then we have our NO2 minus, and we see here our NO2 minus. Let's go ahead and look at the conjugate of that. So again, we're going to look at adding an H plus to give us something neutral. Again, we're thinking to get back to neutral. So do we take away a positive ion or do we add a positive ion if we're thinking of our positive or negative ions? So we add an H plus, that gives us HNO2. HNO2 is a weak acid. So that means it will form with the reaction of H2O and NO2 minus. So then we see, okay, well, this is going to affect our pH. Now let's go ahead and investigate, well, what reaction is going to happen here. So we have water. It's going to react with the ion that we said will affect our pH. And what that's going to do is it's going to take an H plus, right? It's a base because it's a conjugate base of our weak acid. It's going to give us that weak acid, which we know will stay together as a molecule in solution. And we're left with hydroxide here. So with our base, we're going to go ahead and make the hydroxide ion. And what that lets us know is that this will have a basic pH. So let's move on to our third one. Now again, we have our calcium ion and our hypochlorite ion. And so then we look at these and we see there is no conjugate per se of acid of this, a base of this acid. We cannot take an H plus away. And so we see that metal there will not react as an acid. So then we go ahead and we look at our other option here, our ClO minus. So we're going to add an H plus to that and we get HClO. Again, we're investigating what is the conjugate, either acid or base, of the ions we have present. And now we see that this is a weak acid. And because we know it's a weak acid, it will form in the reaction with water and ClO minus. So again, let's go ahead and look at what reaction that would be. We have ClO minus reacting with water, and that's going to take a proton from water, and that's going to give us HClO and OH minus. So again, we look and we see we're forming hydroxide ions. That's going to increase the concentration of hydroxide, and that is going to make this a basic solution. So we notice in this case, we have one neutral solution and two basic solutions from these different salts that we would dissolve in water. So now we've qualitatively identified, is it neutral? Is it basic? Is it acidic? Well, let's see what happens when we actually try and quantify the pH that we would see here, and what other information do we need to know? So let's work on this one together. We want to determine the pH of a 0.5 molarity NaC2H3O2 solution. So here, first thing I want to identify is I realize this is a salt, right? It's a metal with another ion. So we got two ions. With this salt, we notice that it's not directly a neutral molecule that's an acid or a base. And so first step, when we're thinking through this, is what ions are formed when the salt dissolves. So we have Na plus and the acetate ion. So this is the same process that we just thought through with our other solutions, right? We go ahead and we see, is there the conjugate base of this, right? Can we take away an H plus? No, we cannot. And so we notice that our Na, we can think of as simply being a spectator ion. It's going to not affect our pH. It'll still be dissolved in part of our solution, but it's just going to be hanging out and watching what's happening with, or maybe our other ion here that's going to react. So now we go ahead and we look, our acetate ion, we're going to add an H plus to that to see what do we get. We get acetic acid. Acetic acid is a weak acid. So that means we know this is the ion that is going to affect our pH. Okay, so check. We figured out the ions that we have, and then we figured out which one is going to possibly produce either hydroxide or hydronium. And so now we know that. So let's go ahead and do this one here. Let's write out the reaction that we would get. So we have this ion present in solution. It's going to react with water. When it does so, it's going to steal a proton to give us acetic acid. And then we're also going to get the hydroxide ion here. So now we have our reaction. And normally what we do, right, if we're going to, once we have our reaction, we need to figure out what is the concentration of OH minus at equilibrium. So how are we going to do this, right? We normally would go, we'd say, let's look at our reaction, our initial, change, and equilibrium concentrations, because we know some information about our concentrations that we have here. Well, this goes back to, if we think about this ion dissociating our sodium acetate, if I'm going to get 1 mole of sodium and 1 mole of acetate in solution, the concentrations I'm going to have is the same as our original concentration, because we have this 1-to-1 mole ratio when it dissociates. So that means we know the concentration of our acetate ion that we originally start with. So we have a concentration of 0.5 molarity. We didn't directly add in these two ions, or in this case, the neutral acetic acid. So we're going to decrease by some amount for our reactants and increase by some amount for our products. So we get 0.5 minus X and X and X for our concentrations. Now, what we usually do now, or what we've done previously, is we said, well, what is the Kb? Again, Kb, indicator that this is the Kb, not a Ka, is that we're producing hydroxide, right? So this is a base ionization reaction. We need the Kb for our acetate ion. Well, what we would do is we go to a table and we would notice, wait, there's no Kb listed for the acetate ion. So what is this? How can we identify this? Well, and one really key important thing here, when we are dealing with an acid-base conjugate pair, what we'll notice is that the Ke of the acid times the Kb of our base is going to be equal to Kw, the water ionization, autoionization constant. So that means if I know the Ka of our acetic acid, we have the ability to determine the Kb of our, in this case, the acetate ion. So let's go ahead and do that together. So again, the Ka for H2C2 H3O2 times the Kb for its conjugate acid is going to equal Kw, right? 1 times 10 to the negative 14th. Well, I go to a table and I find that the Ka for acetic acid is 1.8 times 10 to the negative 5th. So now I also know the Kw, 1.0 times 10 to the negative 14th. So let's go ahead and plug that in here. I'm going to rearrange this a little bit to be Kw divided by Ka. So that's going to be 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. And so we're going to get a K value, in this case a base ionization value, Kb, 5.6 times 10 to the negative 10th. So now we have the K value for our equilibrium reaction here. So now what we can do is we can go ahead and input the values that we have set up for our equilibrium concentrations. So let's go ahead and rewrite that. So we are Kb. Let's go ahead and explicitly write out what these are. Our acetic acid concentration, the hydroxide concentration, our products, divided by the acetate ion concentration. And then what we're going to do is we're going to go ahead and plug in the values that we have here. So we're going to have 5.6 times 10 to the negative 10th equals X, X, and then 0.5 minus X. Let's see if we can save ourselves a little bit of time and maybe simplifying the math that we have here. Again, we compare these two values. Is there 10 to the third difference? Basically, is our concentration 10 to the third times greater than our K value? And we see, yes, it is. This is actually 10 to the ninth times greater, so that means we can go ahead and simplify this and remove that minus x, because effectively that approximately still equals 0.5. And we're going to see maybe when we calculate this if this approximation makes sense. So now this will go ahead and simplify to 5.6 times 10 to the negative 10th equals x squared divided by 0.5. We do a really quick algebra calculation, and we would get x equals 1.67 times 10 to the negative 5th molarity. Again, once we get to this point, we got to figure out what is that the concentration of. Let's trace it back here. It's the concentration of the acetic acid, but also concentration of the hydroxide ion. So that means now I know the concentration of the hydroxide ion. Well, once we've had a chance to identify the concentration of our hydroxide ion, we go ahead and we see, well, that's going to get us the ability to quantify pH, right? That's what we're trying to figure out. A couple different paths we can follow here. Let's go ahead and just do one of them. So I know the hydroxide ion concentration. Let's go ahead and calculate pOH, negative log of our hydroxide ion concentration, so negative log of that 1.67 times 10 to the negative 5th. Our pOH is going to be 4.776. And we also know the sum of our pOH and pH equals 14. So now I can go ahead and solve for our pH now that we know what our pH is. 14 minus 4.776, and we get a pH of 9.224. Now let's go back and make sure, does this make sense with our original conclusion that this solution would be basic? Yes, this solution is basic, and that is because we have this weak base, the conjugate base of our weak acid, the acetate ion that is going to react with water to give us hydroxide ions, and we're going to be at that pH there. Well, now that we've had a chance to kind of think through this one all together, why don't you go ahead and let's do a quick pause and practice, or maybe it might not be so quick because it might take us a little bit of time to think through this. Why don't you go ahead and calculate the pH of a 0.0250 molarity NH4Cl solution. So go ahead and think through this one on your own. The more you're able to process through this without coming back and looking at what I worked on, the better for you. So I'll go ahead and pause it. And why don't you go ahead and work this out, calculate what your pH is, and then come back and check and see if you got the same thing that I did. So now that you've had a chance to think through this, we again look at the fact this is a salt solution. We get NH4 plus, Cl minus. This is one that we already looked at earlier in this video, and we see that NH4 plus, if we take away NH plus, we get NH3, which is a weak base. That lets us know this is going to act like a weak acid. Let's go ahead and look at our other ion. We get HCl. We see what is the conjugate acid of this base that we could possibly have of the Cl minus ion. And we notice that that is a strong acid. So that means that acid is not going to want to form. Chloride ion is not good enough of a base to steal that proton away from water. So that lets us know that's our ion that's going to affect our pH. So next step, we want to go ahead and make sure we write out how is it going to affect the pH? What reaction is it going to undergo? So we have our ammonium ion. It's going to react with water. And when we do that, it is an acid. So that means water is going to act like a base. It's going to accept our proton. So we get NH3. And we took that H plus away from NH4 plus. And then we get H3O plus. So this should be an acidic solution once we end up calculating our pH. It should be less than 7. So let's go ahead and fill out our rice table here. Reaction, initial, change, equilibrium. So we have a concentration of 0.0250 molarity. Again, the same as our salt because it's a 1-to-1 ratio when it dissociates. We didn't directly add in those two species, the ammonia or hydronium. We're going to increase by some amount of our products, decrease by some amount of our reactants. So we get 0.0250 minus X, and then X for our concentrations here. Now again, once we do this, we need to plug this into the Ka for NH4 plus. Well, again, we go to a table and we notice we don't see that. But what we do know is that the Kb equals 1.76 times 10 to the negative fifth for its conjugate base, NH3. So now we're going to use the fact that we know the product of these two is Kw. So let's go ahead and solve for our Ka now. So our Ka will be Kw divided by Kb. Again, for this conjugate acid-base pair, 1.0 times 10 to the negative 14th divided by our 1.76 times 10 to the negative fifth. So we're going to get a Ka for our ammonium here. It's going to be 5.68 times 10 to the negative 10th. Well, now we have our K value. We have the ability to go ahead and plug in our expression into that K value. So let's go ahead and do that. Take all that information and move it in over here. So our Ka is going to be equal to our product concentrations are divided by our reactant concentrations. So let's plug in the numbers we have. 5.68 times 10 to the negative 10th equals x over 0.0250 minus x. And again, if we thought about this when we were working on this on our own, we'd see we can make that approximation where that is effectively 0.025. So we get x squared divided by 0.0250, and that equals 5.68 times 10 to the negative 10th. So now we go ahead, do a little quick algebra calculation, and we get x equals 3.77 times 10 to the negative 6th. Again, we go back and we think, what species is going to affect our pH that we are producing here? And we see that is the concentration of our hydronium ion. So now we have the ability to calculate our pH, the negative log of that value, 3.77 times 10 to the negative 6th. And so we would end up getting a pH of 5.424. And we go back to our original prediction that this would be acidic. Our pH is less than 7, so that makes sense. That is a normal value, a value that would make sense to us as we're thinking about our pH for this solution. So hopefully now we have a chance to think about our salt solutions, and this adds one more type of solution that we have the ability to think through the pH with relative to either a strong acid, a weak acid, a strong base, a weak base, and now a salt solution. In our next video, as we continue thinking about this, we get the opportunity to think about, well, what happens if I have a weak acid and I throw it in its conjugate base in a salt, or I have a weak base and I throw in its conjugate acid in a salt. And we're going to think about how do those two interrelate and relate to each other in solution.